Greetings, Math 111. This is section 8.2. So we're going to continue our discussion on estimating mu. This time is a little more of the reality that if we don't know mu, we don't know sigma. So the population mean is what we're estimating, and part of our assumption is we don't know the population standard deviation. So that's where we're going. We're going to introduce a new chart today. It's the T-chart. All right, let's jump in. And I'm going to pull my camera just a little closer. I feel like I'm kind of far away. And, all right. Oops, I turned my clicker off. Thought I turned it on. All right, so we're going to use, so again, in this case, to estimate the mean, so we'll have a sample mean, so that's X bar, and we're going to estimate mean. We did, the first time we said we needed to know sigma, but now, and again, this is more reality, we are going to use the sample standard deviation to do this calculation because we don't know sigma. So this is called the student's T distribution, and this is a funny story to me as to where that name came from. So there's a gentleman, Mr. Gossett, back in 1908 that came up with this process, and he worked for the Guinness Brewing Company, but they wouldn't let him publish his results or his findings, or I mean, this is like a whole new way of approaching something, and he wasn't allowed to publish it, and so but he felt like it was important, so he published it under student. Now, I think I could have come up with another name, but that's what he used. So that's why it's called the student's T distribution, is because Mr. Gossett picked that name. So what's interesting is it's very similar to the normal distribution, has a little bit of difference. We'll look at a picture, a diagram that shows the difference. And the other thing that's interesting, it's dependent on the sample size. So things change based on that sample size. So instead of Z, we're using T. So T equals X bar minus mu over S divided by the square root of N. Now, very similar to what we did with Z, where Z was X bar minus mu over sigma divided by the square root of N. So almost identical. Now the interesting thing, there's a new thing called the degree of freedom. So degrees of freedom. And it's outside the scope of this class to get too deep into that. All you have to know is that the degrees of freedom, we shorten that by df, is n minus 1. What is n? N is how many are in the sample, okay? N is how many are in the sample. So we'll need that. Our chart actually, that's part of reading the chart, is that degrees of freedom. So when we use a T distribution, we'll assume that the X distribution is normal. Very similar to when we use Z. We had a Z distribution. Again, the degrees of freedom is n minus 1. So here is that graphic I talked about. See the pink line? The pink line is the normal distribution. Remember, the peak is above mu, and when we convert to Z, that's a 0. So it's mound shaped, it's symmetrical, you know, it looks like sand in a pile. And the tail gets real thin, but never quite lands. When I have a T distribution, very similar, mu is the highest point, it's in the middle, it's mound shaped, it's symmetrical. However, these tails are thicker. There's more out at the ends that could happen. So that's the tails. The other thing is, based on the degrees of freedom, this changes. So my, let's see, the black line, remember, the smaller the sample size, the less certainty. So it's more spread out in this case. So that's the black line. The blue line, the standard deviation is a little smaller. The normal distribution, that pink line, is even less spread out. Interesting thing is, the T chart when we get to degrees of freedom of 30 or more, it looks really, really, really similar to the Z distribution. So there comes a point where the T and the Z are almost identical. All right, so very similar to the Z, the distribution is symmetric about the mean 0. The distribution depends on the degrees of freedom. It's bell-shaped, but it has thicker tails than the Z distribution. And as the degrees of freedom increase, the T distribution approaches the standard normal distribution. And the area under the entire curve is 1. So it's very, very similar to the Z. So how do we find those critical values? Let's jump over and look at our T-chart. Again, this is published or posted on Canvas. It's also in the book. You can pull it, all kind of places where you can take this. But how do we read this? So this is the T distribution. So here, this first column, my DF, my degrees of freedom. This is my confidence. So remember when we, in 8.1, we first started talking about a confidence, we might have 80%, 90%, 95, 99. That's these values here. So here is 99%, this is 99.9%, 98, 95, 90, 85, so forth. So each column is a different confidence level. For chapter 8, we are only using this row next to the C. In chapter 9, we'll get into these two top rows. So, but for chapter 8, we're only in this row. So I have my degrees of freedom. I have my confidence. So remember, those are percentages or probabilities. And then out in the center are my T values. So remember back on your Z chart when I said, make a note, these are Z values and these are probabilities. The T chart is inside out. So that's why I wanted you to do that. So this is degrees of freedom. Again, feel free to write on your paper, put a little note that this is degrees of freedom. These are some sort of probability or percentage. And then these values out in the center are my actual T values, analogous to my Z values. All right, let's jump back in. So that's my, and again, very similar to the Z, this confidence is this area under the curve in the center. One note, so if degrees of freedom is n minus 1, just make sure you keep track when you're doing your formula. This is n, not n minus 1. If for some reason that degree of freedom you need is not on there, go to the next number smaller, okay? So here's kind of a snapshot of that chart I just showed you. Here's my degrees of freedom, here's my confidence, and these are T values. So let's pretend that I wanted a 99% confidence level, so that's this column, for a T distribution with sample size of n equals to 5. If n equals 5, then my degrees of freedom is 4. Remember, it's n minus 1. So come across this row all the way over to the 99. So my T value is 4.604. Okay, remember T values and Z values are similar. All right, they're just describing what we just did. So doing confidence intervals for mu when sigma is unknown. So now you have to ask yourself the question, do I know sigma or do I not know sigma? And they'll tell you in the problem, okay? So I have an error formula. Again, it looks very, very similar to the one with the Z value. Let's write down that Z value option. So it was error equals Z sub C sigma over the square root of n. Okay, that's my error formula for Z. My error formula for T is error equals T sub C standard deviation of a sample, so S divided by the square root of n. Again, make sure you use n. This is not n minus 1. I know that sounds silly, but you just did n minus 1 to find the T value. Sometimes it's tricky to remember to use n here. All right, let's keep going. So we have some requirements, and remember the thing about the 30 If we don't know that x comes from a normal distribution, then we need to have a sample size that's a little bit bigger. So I have x bar minus the error is less than mu, x bar plus the error. That's my confidence interval. We want to say, we're trying to estimate what mu is. I have a piece that's smaller, a piece that's bigger, so I come up with some sort of range of values. That's the confidence interval. My error is t sub c, s times s divided by the square root of n. Some sort of confidence level, somewhere between 0 and 1, usually more like 0.8, 0.85, those kind of things, 0.99. And then my t sub c, t is like z. So let's say an archaeologist discovers 7 fossil skeletons from a previously unknown species of miniature horses. Reconstructions of the skeletons of these 7 miniature horses show the shoulder heights in centimeters. So these are the values. Now, remember how we did standard deviation? Back a couple chapters in Excel or on your calculator. Brush that off, make sure that you're still good at that. Because you may be given raw values and you need to calculate x bar and s. So know how to do that. So here's the mean for these values. What do we say? How many? 1, 2, 3, 4, 5. Oh, 7. So here's my x bar, here's my s. There are 7 values, so n is 7, so degrees of freedom will be 6. And they tell us that it's approximately normal, so it's okay that there's only 7 values. We want to find a 99% confidence interval for mu. I already talked about that. So n is 7, degrees of freedom is 6. My confidence is 0.99. So when I go to my t-chart, so let's do that. I want to go to the real one. They'll show us a sample, but I want to show you the real one. So I have, let's see, n minus 1 was 6, and was it 90? Oh, I don't know why I can never remember. What was the percentage? Seems like it was 99. Yep, 99. There it is. 99. So n minus 1 is 6. We go over to 99. Notice that this is 0.99, this is 0.999. So just keep track of that. So I have 6.99. So my t value, which is this value up in the center, is 3.707. Okay. Let's jump back in. So sure enough, we found the same t value. It is 3.707. So I substitute that into my error formula. Find out that my error is about 1.67. Again, caution, caution, caution about rounding, okay? In this case, this is a PowerPoint. We want to make it look pretty. We round it. But truthfully, it would be best to just use this whole thing and recalculate it both times for my error. The other option is to leave yourself 5 or 6 decimal places. That is a pretty good approximation. So I'm going to take x bar that I calculated, subtract the 1.67, x bar plus the 1.67. So I come up with a range of values, 44.5, 47.8. So these miniature horses, based on that sample, okay, that's the height of these miniature horses, okay? That's the real height, the population. Now, obviously, if they're extinct, I can't go measure the height of all those horses. So here's a great example of how you might apply that. All right, so interpretation, the why. Archaeologists can be 99% confident that an interval from 44.5 centimeters to 47.8 centimeters is an interval that contains the population mean mu for the shoulder height of this species of miniature horses. Okay, again, this is a confidence interval. When your homework or your test says confidence interval, we're taking a value less than mu, greater than mu, and making a so here is just a little diagram to help focus you. How do you know if you use Z or T? If sigma is known, use Z. If sigma is unknown, you use T, and you have to do the degrees of freedom. All right, have a great day, guys.